This is section 3.9, and I'm going to do both days 1 and 2 in this one video since day 2 is short. You received in your email a PDF for an investigation for 3.9, and that investigation had to do with taking the functions e to the x and natural log x and using your Math 8 key to find the derivative values of those two functions for several values of x, kind of like we did with sine and cosine, so that we can discover the derivative of e to the x and the derivative of natural log of x. And if you haven't done that investigation, you should stop the video now and go back to your email and finish out that investigation. Now that you've finished out the investigation, you can continue with the video. So this is the first portion of your investigation, and it is taking the function e to the x, and e to the x has these values for this domain. And what we're going to do is you should have used the n-deriv key, so the Math 8 key, to calculate the derivative of e to the x, and recorded those values. So to calculate the derivative of e to the x when x is -4, you do n-deriv e to the x, comma x, that's your variable key, comma -4. That's the older operating system on your TI. The newer operating system looks like this. It looks more like the Leibniz notation. So that value for -4, then and here's a tutorial page to plugging into each of those values. So you do that for -4, you get a value, you put it here, then you come back and put the same notation in again, and instead of -4, x is -3, you put that value here, and so on to complete the table. And so here's, like I said, here's this calculator syntax for completing that investigation. And then as we record the values of the derivative over the same domain, what we find is that these values for the derivative are identical to the values for the function. So what we find then is the derivative of f of x is actually also e to the x. So what does that mean? Well, in other words, if we come back to the original function, where the function's value is, so let's take a look at when x equals 0. We know that e to the 0 power, e to the 0, is 1. So the function value is 1. What that also tells us, if we go over here to the derivative, is that when x is 0, the value of the derivative is also 1. In other words, if I would draw a tangent line right here, the slope of that tangent line would be 1. That's what this is saying right here in this part of the table. So the cool thing is that for the function e to the x, every point you go to, the derivative and the y value are the same value. So you can see that the derivative value, this table, and the y value are the same. So the y value on the function is 1, the slope of the tangent is 1. Right here, that's about 2.7, so that's a y value of e, because it's e to the first power. It also has a slope of e, or about 2.7. So we come to this conclusion then that the derivative of e to the x is itself. So that's kind of nice because it's easy to remember. And what we're going to really do is we're going to apply that knowledge, since that's what we discovered numerically in the investigation, and we're going to incorporate the chain rule. So a lot of times what happens when we have e to the x is a lot of times the power is actually something a little more complicated than just x. So we consider that the inside function. We could actually even put little brackets around it, little parentheses around it. And so we have the derivative of the outside, which is just itself, times the derivative of the inside. So we can incorporate the chain rule using to find the derivative of e to a power that's more complicated than x. For instance, like e to the 3x. So just to kind of recap, the derivative of e to the x is itself. And so let's do a little more complicated one. Let's do e to the 2x to the -2. That's 2 over x squared. So so I'm going to think about this as being the inside function. So I'm going to put it in parentheses. So my outside function is e to a power, and my inside function is the power itself. So we know that when we use the chain rule, we have the outside derivative times the inside derivative. So just like, coming back to this example on the left, just like e to the x, the derivative is itself, I want you to think that same thing when we talk about the derivative of more complicated powers. So the derivative here is itself. So you just write what you see. Itself times the derivative of the inside. So e to the x, the derivative is e to the x. E to the 2x to the minus 2 power, the derivative is e to the 2x minus 2 power times the derivative of the inside. So if we look at this inside, it's 2x to the minus 2. We're going to bring the minus 2 down, multiply it by 2 to get minus 4, and then reduce this power by 1. So it's a minus 3 power. So this is the derivative of e to the 2x minus 2 itself times the derivative of the inside. And so I'm just going to clean this up a little bit. I'm going to take this and put it down in the denominator, and I'm going to make this power fractional. So this is the derivative of this problem. So if we want to evaluate that when x equals 1, I'm going to put 1 in for here and 1 in for here. And I'm going to evaluate this. So this is minus 4e to the second power over 1, which is just minus 4e to the second power. And if we would calculate that, you know, e is about 2.71. If we square it and multiply it by minus 4, we get about 29 or maybe close to 30, just to kind of give you a decimal equivalent. So let's use the chain rule with this, but we're also going to need a product rule because we have a product of x squared times e to the 1/6 x cubed. So we need to use our product rule here, derivative of the first times the second unchanged. So this is my u, and this is my v, and then plus u, the first unchanged, times the derivative of the second. And when we take the derivative of that second, that exponential, we have to remember that we have an outside and an inside function. So that's where we need the chain rule. Okay, so using the product rule, derivative of this is 2x times this unchanged, so I'm just going to copy it right down here, plus the first function, unchanged, x squared, times the derivative of this. So the derivative of this, again using this chain rule, is the derivative of e to the u is itself times the derivative of the power. So I'm going to write this itself right here. There it is, and then times the derivative of the power. So bring down the 3. 3 times 1/6 is 3/6, or 1/2, x to the 2. So there's the derivative of the power, 1/2 x to the 2. And so simplifying this, the second part particularly, looks like we have an x to the 4th here over 2, and then times e to the 1/6 x cubed. Now looking at natural log. So we did the same thing for natural log that we did for e to the x in the investigation. So here's our natural log. Remember, natural log of whenever we take a look at the x inside the natural log, this has got to be positive. So on your copy, this is an absolute value, I hope. And in other words, we have no negative x's that we're using. We're not using the second and the third quadrant at all. And so as we then use our Math 8 key to take the derivative of the natural log, since we can't take the derivative of any negative values, I took the derivative of a couple of values between 0 and 1, and then some integer values beyond 1. So doing an n deriv of natural log of x for 1/4 gives us this, and as we go through and take the natural log of the derivative of the natural log of all these values, this is the relationship we see. So using n deriv when x is equal to 1/4, the n deriv of the natural log at 1/4 is 4, so I would graph that point, and then when x is 1/2, it's at 2. So you notice a unique pattern here, and you can even notice it better when you make sure that these are fractions. as you calculate the derivative of natural log for 2 through 7, then we find that the derivative itself is just the reciprocal of all the x values. So the derivative of natural log of x is 1 over x. And so that is the derivative of the natural log of x, as the data shows in the table. And so really what it comes down to is incorporating the chain rule. So if when we look at the natural log here, if we take the derivative of the natural log, it's 1 over whatever we see in the brackets times the derivative of the brackets. Just really similar to e to the x. So the natural log of x, the derivative is just 1 over x. It's 1 over what you see in the brackets. No chain rule is necessary because the chain rule would be dx over dx, which is just 1. Here's where we need to use the chain rule, where we have something more complicated than just a straight up x. So here we look at this as the outside and the inside function. So the derivative then is 1 over whatever's in the brackets. So it's 1 over, it's the derivative of the outside times derivative of the inside. So it's going to be 1 over 5x times the derivative of the inside, which is 5. And if we simplify that, we find that it's 5 over 5x, which equals 1 over x again. So it's kind of interesting, but it happens to be that when you have a linear inside function, you still get the same derivative as if it was just ln x. That'll happen every time with anything linear on the inside. Let's take a look at when it's not linear on the inside. So 2x cubed. The outside function is still natural log. The inside function is now 2x cubed. So our derivative is 1 over, again, the outside times the inside derivatives. It's going to be 1 over whatever's in the absolute value. So 1 over 2x cubed times the derivative of the absolute value, which is going to bring down the 3 to make a 6, x squared. So the derivative is the outside derivative is 1 over 2x cubed. The inside derivative is 6x squared. When I simplify that, the 6 and the 2 cancel to give us a 3, and we've got some powers canceling here, so we end up with 3 over x. So as you get a more complicated inside derivative, you get some more complicated possible canceling here. At this point, you're done with day 1. And you can start the day 1 homework. I'm going to continue the video and go into day 2 because it's pretty short. So this is the beginning of the day 2 video. And so day 2's video is to look at this relationship. We know that the derivative of e to the x is e to the x. In other words, we know that e to the x is its own derivative. And that happens just because of e to the x. So the question is, what is the derivative of a to the x? In other words, instead of this being e, maybe this is pi, or maybe this is 4. A is just some numeric value. So we know that if we have e to the x, its derivative is e to the x. What about if we have pi to the x? That would be, e to the x is about 2.71 to the x. Pi would be 3.14 to the x. Or how about just 4 to the x? What are those derivatives? So in order to look at this, we're going to look at 4 to the x. We've got to kind of identify a few things. First of all, the large number out front, is we call that the base. And then the exponent, the x is what we call the exponent. So let's look at 4 to the x and take its derivative using the chain rule. But the only thing we really know how to take the derivative of is e to the x. So we're going to rewrite this so that it's e to a power. So this is kind of tricky, but it goes back to exponentiation and our logarithmic identities back from Algebra 2 and Trig. So for instance, since e and ln x, natural log, are inverses of each other, if we exponentiate and then take the natural log of 4 to the x, e to the ln powers, this is an identity that means 1. So we can rewrite 4 to the x power as e to the natural log of 4 to the x power. Means the same thing. And the reason why this is helpful is because we can take the derivative of e to a power using the chain rule. So that's what we're going to do to this. Before we do that, we're going to bring the x down because this is a power. We can bring that in front of the natural log. And so we're going to bring that power down. So now we literally have e to a power. Now remember, the natural log of 4 is just a number. It's a little bit bigger than 1. So to take the derivative using the chain rule, this is just going to, taking the derivative, this is not going to be that bad. So here we go with the chain rule. So we know the derivative of e is itself. So when we differentiate this, I'm going to call this the inside function, x to the ln 4, and then I'm going to call my outside function e to the u. And this is going to be a little easier to take the derivatives in. So the derivative then is the derivative of x times natural log of 4 is just natural log of 4. Think of u as being something like 7x, right? Then the derivative would just be 7, the coefficient, that value. ln 4 is just a value. So the derivative is just ln 4. The derivative of e to the u is e to the u. So I've got the derivative of the outside, e to the u, derivative of the inside, natural log of 4, and I'm just going to multiply those together. So here's the derivative of e to the x natural log 4. I'm just going to put the substitution back in here, and there's my derivative. So just to kind of recap this whole page, I exponentiated so that I could get an e to the x function. That I know because I know how to find the derivative of that. And so this whole bottom part of the page is using the chain rule to find the derivative of that exponential. So I'm going to change the screen now, but you're going to still see this. So here it is. So let's kind of go back and rearrange it to see what we have. I'm going to take this and put it back in the power spot. And I'm going to use my identity again to call this just 4x. So the derivative of 4 to the x power is 4 to the x power times the natural log of 4. So really what happens truly is when we take derivatives of exponentials, like 4 to the x, we just need a multiplier out here. And the multiplier is the natural log of the base. So let's go back and think about e to the x then, and apply this rule and see if it works out. So the derivative of e to the x is going to be itself, e to the x times the natural log of e. Think about the natural log of e is just 1. That's why it was so easy to see that the derivative of e to the x is just e to the x. That's why it was really easy to see that on a graph, because it's really e to the x times natural log of e, which just ended up multiplying e to the x by 1, so it didn't end up changing it at all. Since we changed the base to something other than e, like in this example, 4, if I had you graph the derivative of the derivative of 4 to the x, you wouldn't be able to recognize it as 4 to the x times the natural log of 4, because this natural log of 4 would have distorted the graph. So let's think about another example here. Let's think about 7 to the x power. So the derivative here then is going to be itself times the natural log of the base. So 7 to the x times the natural log of 7 would be the derivative of that. So our derivative for exponentials for any base, including e, is taking the derivative of a base to a power, so a to the x, is itself. You notice we see the original expression in the derivative, so it's itself times the natural log of a, or the natural log of the base. So let's try the chain rule with this. So we know that the chain rule is going to be taking an outside derivative times an inside derivative. So the outside derivative is our exponential derivative. Our inside is going to be something like a power rule or something like that. So I'm going to think about that as my inside function. I'm going to think about that as having brackets around it. And so that's going to be my u. So my y is just going to be 2 to the u minus 3. So the derivative of my inside function is 2x. The derivative of my outside is just going to be itself times the natural log of the base. So itself times the natural log of the base, and then the derivative of this is 0. So putting these two things together, multiplying them together, here's my outside, there's my inside derivative. It's going to look like this. And then doing the substitution back here, I'm going to put the x squared back. So there's the derivative of 2 to the power x squared minus 3. And then this is just rearranged a little bit. So just to kind of recap here, we've got 2 exponential derivatives. We've got our general exponential derivatives that works for any exponential expression. And then we've got the special situation for e. And then we've got the derivative for the natural log. So these two on the left we discovered in our investigation. This is, I don't even think is on your paper at all. We've removed this material from AP testing, so that's not necessary to know. So at this point you should be able to do both days 1 and day 2 of the homework for 3-9.